In this video, I will define Taylor polynomials. If you look at different books, you will find many equivalent ways to introduce Taylor polynomials. The definition I've chosen illustrates very well where they come from and why we care about them, although it is not the most helpful for computations. In later videos, I will transform this definition into other equivalent versions that are better suited for computations, including an explicit formula. My goal is to approximate functions with polynomials. Why? Because polynomials are simple and they make everything easy. Let's say I have a function f, and a is a number in its domain, and I want to find a polynomial p such that p of x is close to f of x when x is near a. In other words, the polynomial is a good approximation for the function near a. We already know an example of this, the tangent line. For example, here is the graph of a function and its tangent line at a. And we know that the graph of the function and the graph of the tangent line are close to each other as long as I stay near a. Of all the lines that intersect the graph of the function at x equals a, the tangent line is the best approximation near a. But what does that mean? I would like to know what being a good approximation near a actually means so that I can construct other polynomials that are even better approximations of the tangent line. For this purpose, I'm going to define the remainder or error as the difference between the function and the polynomial. This difference is literally the error I make when I use the polynomial instead of the function. And I want this error to be small. But I will need something more precise than merely saying small. Let's look at the tangent line again. Here is a value of x, and here is the remainder at x. It is this difference. Let's explore. What's special about the tangent line? I said I wanted an approximation near a, so perhaps the condition is that the remainder at a is 0? No, that's not enough. There are many other lines that also give error 0 at a, and some of them are very bad approximations, so that's not it. I need something else. Well, I want the approximation to be good when x is near a, not only at a. Perhaps what I need is for the limit as x approaches a of the remainder at x to be 0. No, that's not enough either, because all these other lines also satisfy that the limit of the remainder is 0. Then what's special about the tangent line? What I need is for the remainder to approach 0 fast. All of these lines satisfy that as x approaches a, the remainder approaches 0, but the remainder for the tangent line approaches 0 faster than for any other line. That's the key. But of course, this immediately leads to another question. What does it mean to approach a limit fast? How do I measure how fast a function is approaching its limit? I need a scale. Fortunately, I have one. For simplicity, first let's focus on the case a equals 0. This is the graph of y equals x. As x approaches 0, y approaches 0. Now compare it with y equals x squared and with y equals x to the 6. They all approach 0 as x approaches 0, but some do it faster than others. Look how flat the graph of x to the 6 is. As x approaches 0, every positive power of x approaches 0, but the larger the exponent, the faster it approaches 0. Excellent. I'm going to use this idea. I want the remainder to approach 0 fast. To determine how fast, I am going to compare it with powers of x. This leads to the following definition. Let f and g be two continuous functions at 0 and n be a natural number. We say that g is an approximation for f near 0 of order n when, well, that's a lot of variables. Let's unpack them first. F is my original function, g is the function I am using as an approximation for f, 0 is the point near which I want an approximation, and n measures how good the approximation is. Okay, as I was saying, g is an approximation for f near 0 of order n when the limit, as x approaches 0, of the difference of f on g over x to the n is 0. What does this mean? If I write the function f as g plus a remainder, this means that as x approaches 0, the remainder approaches 0 faster than x to the n approaches 0. Why? Look at the limit here in the box. In general, I have an indeterminate form of type 0 over 0, The numerator is the remainder, which has limit 0. The denominator is x to the n, which has limit 0. For this indeterminate form to resolve into being 0, the numerator must win over the denominator. The numerator must approach 0 faster than the denominator. And that is why this is a sensible definition. Great. This works when a equals 0. But what if I am looking for approximations near a different value of a, not just 0? All I need to do is shift the scale. Here is the graph of x minus a, which approaches 0 as x approaches a, and here is x minus a squared and x minus a to the 6th. They look the same as before. To study approximations near a, I will compare the remainder with powers of x minus a, instead of with powers of x. That is all. Other than that, the definition works the same way. This time I begin with functions f and g, which are continuous at a, and I say that g is an approximation for f near a of order n, when the limit, as x approaches a of the difference over x minus a to the n is 0. That is all, and the interpretation is the same as before. This means I can write f as g plus a remainder, and as x approaches a, the remainder approaches 0 faster than x minus a to the n. Excellent. We are finally ready for the first definition of Taylor polynomials. Let a be a real number, let f be a continuous function defined at and near a, let n be a natural number. The nth Taylor polynomial for f at a is a polynomial, which I will call Pn, that is an approximation for f near a of order n. And now we know what that means. It means that as x approaches a, the function minus the polynomial approaches 0 faster than x minus a to the n. And I am also going to request that the polynomial has degree at most n. This requires some explanation. At the moment, the degree seems unimportant. In later videos, I will prove that as long as f has enough derivatives, we can always construct this polynomial, and we can do so while keeping the degree at most n. We can also get other polynomials with the same property and with higher degrees. But smaller degree is simpler, so we prefer it. That's the reason for this requirement. But again, right now this is the least important part of the definition. As an exercise, to make sure you understand the definition, I invite you to check that the first Taylor polynomial gives us the tangent line. I hope I have now made clear what I said at the beginning of the video. This definition explains where Taylor polynomials come from, why we care about them, and why they may be useful. However, this definition is not helpful for computations. Based on this, I have no idea yet how to compute the Taylor polynomials of a function. In the next videos, I will try to rewrite this definition into some equivalent forms that may obscure a bit the meaning of Taylor polynomials, but which are much more useful when I actually want to perform computations. Then I will work out some examples. Stay tuned.